Hello, this is Mr. White, and this video is on natural logarithms, differentiation. Here are the 4 exercises we'll do in this video. So recall from our textbook that, and our classroom discussions of course, that the derivative of ln of some function u, some function of x that we'll call u, is going to be the derivative of u over u itself. Pretty straightforward rule, and the main thing we just need to keep in mind is to use our logarithmic properties as appropriate. Now we look up here, and at first glance you may be tempted to think we can use some logarithmic properties, but there is no log property involving the addition or subtraction here. So this u in here is not too bad. So when we take the derivative of h here, we'll say h prime of x, and we'll put that u on the bottom in the denominator, 5x squared minus 7, and up top we'll simply put the derivative of u, which in this case is going to be 10x, right? And then minus 0, so we don't have to bother with that. So that almost seemed too easy, didn't it? We put a box around it. Let's go ahead and try to check by calculator. And what I'll normally do is just evaluate the derivative on the calculator at some well-selected value of x. Now, the values that we typically would use for x that'd be very easy to plug in would be something like 0 or 1, perhaps. But do notice that neither 0 or 1 are in the domain of the original function. If I put a 1 here, this quantity turns out to be negative, and you can't take the log of a negative number. So we do have to pick an x value within the domain of the function. So notice that plugging in 2, that would be in the domain of the function. This is a positive quantity, which you can take the log of. And wherever that point may be, whatever its y value may be, we're going to calculate what we predict its slope to be. So 10 times 2 up top would be 20. On the bottom, 5 times 2 squared would be 20 minus 7. That would be 13. So I'll bring the calculator on the screen. There's our original function, ln x squared minus 7. Let's just go to zoom standard. So graphing from negative 10 to 10 on both axes. And we see, again, there's that little gap in the middle where there are some numbers that are not in the domain. Let's go to second calc number 6. I'm pressing number 6 on the keypad. And we said we would evaluate at 2, so I just press 2, enter, and I see that the slope there is 1.5384. I'll go to second, quit, and then I'll go to second and then answer. That's the negative sign on your calculator. And there I see that same derivative displayed. And if I type in now 20 divided by 13, which is what we predicted it would be, sure enough, that is the same number. So that seems pretty compelling evidence that we did our derivative correctly. So our boxed answer is correct. All right, on to the next one. Okay, to derive this one, we definitely see a product rule coming up. And we also, again, like I said in the last exercise, we should be mindful of our logarithmic properties going to help us. And I do see an opportunity where we could do a log property and express this as ln of 8 plus ln of x. But honestly, I don't feel like it's going to help us that much in this particular problem. So with experience, you'll learn to determine when your log properties really help out and when they're not that big of a deal. So let's go ahead and derive now using our product rule. We'll do the second function, ln of 8x, times the derivative of the first, so times the derivative of x, which would be 1, plus the first function, x, times the derivative of the second. And just as in the previous example, the derivative of ln of 8x is going to fit the u prime over u pattern. So we'll put the u on the bottom, where u is the 8x, and the derivative of 8x will go up top. And the derivative of 8x is simply 8, right? So we notice that here the x and the x divide out, and also the 8 and the 8 divide out, and we're just going to be left with a 1, a plus 1. So our derivative is ln 8x plus 1. you may put a box around it. Now, alluding to something I said earlier, if this were a textbook exercise and you look in the back of the book, or if this were a multiple choice test and this was not one of the options, here's another thing to consider, another possible way this could be written. Again, you could do your log properties and say that ln of 8x is the same as ln of 8 plus ln x, and then of course plus the 1, of course. And then from there, also keep in mind that you may see it expressed this way sometimes. Recall that 8 is simply 2 to the third power. And according to one of our log properties, that 3 can come down in front. And therefore, our final derivative could also be written as, I'm going to put the variable term first, the ln of x, plus 3 ln 2 plus 1. That's another totally valid answer. So be prepared for either one. So as far as checking with the calculator goes, I'm going to just arbitrarily choose a different method than I showed in the first exercise. I'm going to graph the original function as y1 and then the derivative as y2. So here they are, already pre-entered into the calculator. I'm using these window settings, which I've determined are pretty good for this exercise. I'll graph. And we see the original function is in the bold graph and the derivative is in the non-bold graph. And I'm going to go to second calc and I'm going to press 6 for dy over dx. And I'm going to, again, just choose a random point, at least within the interval on this window. So let's pick 2. And I find that the derivative dy over dx at x equals 2 is 3.7725. So I'll just arrow down onto the derivative curve, and I'll see that the y value of that derivative is 3.7725. So there's another way to check with calculator for derivative problems. Let's go to the third one. Okay, here's one where our logarithmic properties really take center stage and help us out. If we were not to take advantage of our log properties, we would have to take this in computing y prime. We'd have to take this, put it in the denominator of a fraction, and then we'd have to take the derivative of this and put it in the numerator. And taking that derivative would involve, let's see, the chain rule and the quotient rule, and then we'd have fractions within fractions, and it would be a huge mess. Now, sometimes we just have to deal with huge messes in calculus, but if we can avoid it, we should certainly do so. So before we do any calculus, let's just rewrite the original function. And as usual, the radical doesn't really do us any favors. We prefer the rational exponent of 1/5. And again, I'm still sticking with the non-calculus. We're not even going on to y prime yet. We're still working on y, and we're going to use our logarithmic property, our power property, which says we can bring that 1/5 exponent out in front of the logarithm. And then we'll use another log property, the quotient property, which says that for this ln term, I can split up that division. That logarithm of a quotient can be expressed as the logarithm of the numerator minus the logarithm of the denominator. Now, of course, we still have that all with a 1/5 out in front. Okay, so be careful at this point. Again, this is where students will often get a little bit overzealous and try to use log properties to split these up even further. But remember, there is no log property for addition or subtraction. But that's okay, because now I've got something that is going to be relatively easy to derive. If I focus on the ln of 2x plus 3, I'll use that u prime over u pattern. I'll say that's going to give me 2x plus 3 on the bottom, and the derivative of 2x plus 3 up top, that's going to be 2. And of course I am deriving now. I should make that very clear. And when I derive this log expression, I'm going to do the same thing. I'll put the u on the bottom, the 4x minus 1 on the bottom, and the u prime up top. Now, depending on the context of the problem, you may be able to just put a box around it and call it done. But remember, especially for derivatives, that we often want to set them equal to 0 and find critical numbers. And so if you're going to set them equal to 0, you really want to combine these into a single term. So if it turns out you need to do that, we need to do common denominators. So we'll do the 4x minus 1 over 4x minus 1 here, and the 2x plus 3 over 2x plus 3 over here. Now that we have the common denominators, we will go ahead and distribute out these numerators. And of course, make sure you distribute that negative sign. And notice that now the 8x minus 8x cancel each other out, and that numerator will end up being negative 14. So let's go ahead and write y prime equals, we'll put that negative 14 in the numerator. In the denominator, we'll put that common denominator of 2x plus 3 times 4x minus 1. And don't forget this 1/5 out here. That's going to result in a 5 being in the denominator as well. So this is how we'd write the derivative as a single term. So I repeat, either of these box answers, this one up here or this one down here, might be acceptable depending on the context. But the advantage of this one down below is that it's a lot easier to get some clues about the critical numbers. Notice that there are no x values that could possibly make this derivative equal to 0. So nowhere are we going to have a horizontal tangent line. Now it initially appears that there may be a couple x values that are going to make our derivative undefined, and that those could be critical numbers. But notice that those same x values that would make this undefined are also x values that would make our original function undefined. Therefore, they are not in the domain. So bottom line is I can see very easily from this writing of the derivative that there are going to be no critical numbers. And we are not going to have any extrema, any minima or maxima. So let's bring up a GeoGebra representation of the original function. Here's the original function. And again, we see visually here, graphically, that there are no extrema there. It appears that the graph, that the derivative will definitely level off and get very close to 0 as we go to x approaching infinity or negative infinity, but there are no minima or maxima here. All right, let's go on to our last exercise. Okay, differentiation is still the task at hand, but this time we'll do so implicitly because it looks difficult and actually it looks impossible to get y by itself in this particular exercise. I would like to contrast this with exercise number 2 here. Notice that in exercise number 2, we had a natural log that was part of a product, whereas up here in this exercise number 4, we have a product that's embedded inside the natural log. So even though natural log and the product rule are going to be involved in both cases, we're going to find that it feels very different in exercise number 4 than it did in number 2. Okay, let's move that off to the side, and let's recall that with implicit differentiation, we start by deriving both sides with respect to x in this case. And we know that the pattern for deriving the ln term is going to be u prime over u, where xy represents our u function, right? So let's go ahead and put that u on the bottom. Now, if you feel like we're doing too much in one step, I would encourage you to consider this. If you don't want to actually take the derivative of xy, or u in this case, if you don't want to actually take the derivative, at least do this. Say we still need to take the derivative of xy, and we'll handle that derivative in the next step. So again, we still have this clearly documented and correctly documented, the derivative of u over u. All right, the derivative of this minus 3y is going to give us minus 3, then dy over dx, because we have different variables here and here, equals, and on the right side, we just have 5, and we don't need anything after the 5 because we have the same variables here and here. Okay, now in this step, we'll employ the product rule to do that derivative. So the derivative of x times y is going to be the second function, y, times the derivative of the first function, x, plus the first function, x, times the derivative of y, dy over dx. And that all, of course, is still over xy, minus 3 dy over dx equals 5. That hasn't changed. And remember, the objective here is to get dy over dx by itself. So it may be tempting, and it'd be an easy error to make to say, okay, well, I'm just going to factor dy over dx out, side of a big set of parentheses. But here's the problem. Notice that due to this plus sign up here, we really need to consider this and this to be separate terms, and the dy over dx only affects this term. It has nothing to do with this term. So we will do some factoring eventually, but not quite yet. Let's first break this fraction apart into two separate fractions. We'll take y over xy, and we can see that the y's are going to cancel out, and I'll just get 1 over x there, plus x dy over dx over xy. And here we see that the x's are going to cancel out. So dy over dx over y minus 3 dy over dx equals 5. And as far as that idea of factoring out a dy over dx, it looks like we're going to be able to do that with these two terms. We just need to move this over to the other side of the equation. So let's do that. Let's subtract the 1 over x over to the right side of the equation. All right, and now we're prepared to factor out the dy over dx. All right, so here comes the dy over dx and the big set of parentheses, and on the inside I'll have 1 over y, because if we choose to, we can think of this dy over dx being included with a 1 entirely in the numerator to give us this, over this y here, minus 3 equals 5 minus 1 over x. Now we just need to get the dy over dx by itself. And we're getting awfully close to being done here, but it would be bad form to leave our answer involving fractions within fractions. So there are a couple ways you could do this. You could do the common denominator up here, and then a common denominator up here, and then do this fraction divided by this one. But the way I prefer to do it is to say I'm going to multiply this fraction times xy over xy. And do you see why that's going to help us out? Well, it's because when I distribute the xy, it'll resolve both this fraction and this one. They'll both become non-fractions. So let's go ahead and distribute xy times 5, 5xy, and then xy times 1 over x. The x's will cancel, and we'll get minus y. xy times 1 over y will reduce to just x. And then xy times minus 3 will give us minus 3xy. And finally, about the only other thing we could do is then factor the top and bottom. So dy over dx. Up here, let's factor out the y, and we'll get y times 5x minus 1. And then down here, we'll factor out the x, and we'll get x times 1 minus 3y. All right, finally, put a box around it. We are done. Now, unfortunately, I really don't know any way of checking this. At least no way of checking it using the tools we have at our disposal. Even GeoGebra is unable to graph this original function, this original implicit function. So the best we can do is just do our work as carefully as possible, clearly show our work. And if there's an error, well, at least you can count on some partial credit if you at least felt like you knew what you were doing.